Hello, my name is Shashank Shekhar. Good evening, students. So we are doing a 45 days crash course on chemistry for our upcoming JEE exams, and we have done two chapters that were some basic concepts of chemistry and atomic structure. Today we will proceed to our third chapter, which is chemical bonding, on the fifth day. So the first theory which was given for the chemical bonding. So basically there are three theories, three to four theories that we have to cover for the JEE syllabus. The first one is the Lewis structure. The second one is the whisper theory. The third one is the valence bond theory, and the fourth one is the most latest one is the molecular orbital theory. So we will study them one by one more deeply because these are the main four topics of this chemical bonding, and we will see that why these theories were developed and what were their drawbacks and limitations that they were pulled off and new theories were given. So the first one, the most starting one, was the Lewis structure. So this Causal Lewis, the scientist, was the first one to give this theory of chemical bonding, which used mainly the octet rule to define the bonding in the chemical compounds. So what is this octet rule? So you must have learned about this octet rule in your 8th class also. So it says that an atom is stable, or an element is stable as long as it has 8 electrons, like the noble gases we have in the periodic table. So for example, the noble gases like xenon we have, and hydrogen, then helium we have. So hydrogen and helium are exception here because they do not have the power to get more than 2 electrons because of the limited number of energy shells they have. So this was the main approach for the this Lewis dot structure by Causal-Lewis to define the chemical bonding in compounds. So how does it make it happen for the different type of compound? So there are mainly two type of compound that we know, that are ionic and covalent. So he explained them one by one to give this. So what were this theory? So his theory said that suppose we have a compound here, like suppose we have CO2 here, or like we have carbon dioxide here. So if you want to get the Lewis dot structure, then you must be aware about the outer or this outer electronic configuration of carbon. So if you write the electronic configuration of carbon from atomic structure, we have this. So it is 1s2. So carbon has total number of 6 electrons. So it will be 1s2, 2s2, and 2p2. So this is the electronic configuration of carbon from the rules we know about the filling of electrons. So in the previous lecture we have seen the filling of electrons, the rule that govern the filling of electrons. So that was the case. So with the help of it we can get this electronic configuration. Now if you consider it for the outermost shell, then it has 4 electrons, that is, one is in the s subshell, so 2 is in the s subshell, and 2 are in the p subshell. So if we, and for oxygen, if we write here, so oxygen has total number of 8 electrons. So it will be 1s2, 2s2, and 2p, 2 to 4, 4, 2p4. So in the outermost shell, the oxygen has 6 electrons. So 6 valence electrons. And it has 4 valence electrons. Now we have to write the Lewis dot structure for carbon dioxide. So how we will write it? So suppose it is written like this. So carbon has 1, 2. So I'm denoting the electrons, that the valence electron of carbon, using cross. So we do have here the carbon. Now suppose we have the oxygen here. So it has 6 electrons. 1, 2, 3, 4, 5, and 6. Similarly, there will be one more oxygen like this. That is 1, 2, 3, 4, 5, 6. Like this. Now if we see the sharing of electrons, so the carbon will share with electrons with oxygen, and oxygen will do the same. So it will be like this. So the oxygen will take 2 electrons. Similarly, this oxygen will take 2 electrons to complete its octet, because initially it has 6 electrons, so 6 plus 2 8. And similarly for this oxygen, that is 6 plus 2 8. Now carbon also needs to complete its octet. So how it will do? So it will do it like this. Let me draw it with a different one. So this one is the color we are taking, and in this fashion it can complete its octet. Now this carbon dioxide is completed, and all of its elements, this oxygen, this both oxygen and this carbon, have completed its octet, as it has 8 electrons. This 1 2 3 4 5 6 7 8. Similarly this oxygen 1 2 3 4 5 6 7 8. So it is the correct Lewis structure for this CO2. Now there were some limitations of the octet rule, so it cannot explain many of the theories. Although it was the most starting and the primitive one, it could explain that why this compound is formed or why that compound is stable, but it could not explain many of the things. The first one was the hypervalency or the hypovalent. So what do you mean by hypervalent or hypovalent? So some of the compounds, suppose we have a sulfur here, element like sulfur, and if we consider, then we can have boron. So they form compounds such that they have more than 8 electrons in the valence shell. So suppose we have SF6. So if we draw the Lewis draw of the structure, so it has 6 electrons in the outermost shell, as atomic number is 16. So it will be 1s2, 2s2, 2p6, 3s2. So 6 plus 4 10, 10 plus 2 12, 3p 4. So you can count it, 6 4 10, 10 6 16. So what is the outermost shell for sulfur? It is 3. So the total number of valence electron will be 6. 4 plus 2 6. So sulfur will have 6 electrons like this. 1 2 3 4 5 6. Now we have 6 fluorines here. So fluorine has a number of 7 electrons in the outermost shell. So I will do it like this: 1 2 3 4 5 6 and 7. Again 1 2 3 4. So let me denote it with a dot rather than a cross. So it is 1 2 3 4 5 6. Again 1 2 3 4 5 6 7. Again 7. So 3 3 6 1 7. Similarly 1 2 3 4 5 6 7. It is again 1 2 3 4 5 6 7. Same goes for this and for this fluorine. So if fluorine wants to complete its octet, it will do it like this. So it will take 1 electron from sulfur. This fluorine will also take, and like this all of this fluorine will complete the octet by getting 8 electrons in total. 7 plus 1, that is 8. Now the sulfur will take back all the electrons, means they are in the sharing mode. So it will get all 1 electron from each of this fluorine atom one by one. Now if you count the total number of electrons that are present in sulfur, then it will be 6 plus 6, 12. So you can see here clearly that S orbital is having, means this sulfur is having more than 8 electrons. The reason is that it has an empty d orbital, because we have moved to the third cell, and for third cell we know that n is equals to 3. So L will go from 0 to n minus 1, so which will be 0 1 2, and this d means we have the d orbital. So by this we can say that it has d orbital, that is, it has an empty orbital, that is 3d. Although this 3d will be not filled first, if there is one. So 4s will field first, we know the energy rule. But there is a 3d orbital or the 4s, so it can get their electrons there. Due to this, it is a hypervalency. So sulfur shows here the hypervalency. So what is hypervalency? By hypervalency we mean that it has more electron than the octet rule, that is more than the 8 electrons. So hypervalency means more than, greater than 8 electrons. Electrons are greater than 8. Number of electrons are greater than 8. Now some of the compound shows the that is called hypovalency. So what is hypovalency? So it is just the opposite of hypervalency, in which that compound will have the lesser number of electrons as compared to the octet rule. So if we take the example, then we have BeCl2. So BeCl2, or we can take another example for boron also. Boron also shows the same. So these are the reason that the octet rule could not explain some of the compounds like this. This was the first reason. The second reason, it says nothing about the structure. So if you see a compound, it must have some structure. Means if you consider this fluorine here, all these fluorines here, so it must be oriented in some direction. It cannot be random, that it cannot be on the plane. All of the fluorine cannot be on the plane, or rather all of the one of the fluorine is upward towards you, or towards towards the board. So we cannot see the structure defining any structure defining quantity in the octet rule. So this was the second drawback. Now the third drawback was it could not explain bonding in noble gases. So some of the noble gases can also show bonding. So according to octet rule, if a element has complete its octet, that is 8 electrons, then it will not form any bond. So noble gas are the most common example of it. So helium and this, you can say xenon and many other gases must not have formed the bond. But if you can see that many of these elements can form bond. So let us take an example. So the first example is XeFF6. So XeF6. So xenon is a noble gas. Noble gas. So it must have complete octet. So it has 8 electrons in its outermost shell. But although it has a complete octet, this xenon will form a chemical compound, that is XeF6, that is xenon hexafluoride. So due to these reasons, this Lewis approach was declined, and then the other theory that came into the light was that of Vesper theory, that is valence shell electron repulsion theory. So we will study that in the later slides, later lecture. So before that, let us see that how it explains the bonding in ionic compound and covalent compound. So if your suppose we have a compound, then it can be either ionic or it can be either covalent. So this percentage of ionic and covalent will change. So by this I mean that, so do not get confused that okay sir, sir has told a compound that is ionic, so it will be ionic. It is not the case. A compound can never be 100% ionic or 100% covalent. It will have some covalent character as well as some ionic character. But we take the majority thing. So suppose we are taking an ionic compound, that compound that is majorly ion, present in the form of ion, suppose like NaCl. So first of all, the first property of this majorly ionic compound is that it is non-directional in nature. Means this Cl minus can be at any place. Means it is not defined. It is completely based upon the electrostatic force of attraction. So the ionic bonds are non-directional, first of all. Now second is that, so how does bonding take according to this octet rule? So you must have studied that sodium is a metal since, so it will have a tendency to donate electrons, while chlorine is a non-metal, so it will have a tendency to accept electrons. So it will have this kind of bonding. So Cl has 6 electrons, 7 electrons, sorry, and sodium has 1 electron in the outermost shell. Now this sodium atom will donate 1 electron to its neighboring chloride ion like this. Now this chlorine will complete its octet, and sodium will be also completed. So this will be Na plus, as it is donating electrons. So one negative charge is going towards Cl, so it will be Na plus, and this will be Cl minus. So in this way, an ionic compound is formed according to Lewis dot structure. So the same thing is written here, that it is non-directional in nature. Yeah, that is so. And the second thing, it is the ionic bond donate electron. So we have seen that it has donated one electron. Yeah, one more thing here, it is written that the positive ion is called the cation, while the negative is called the anion. So this thing here is called as cation, and this is called as anion. Okay, so this is cation and this is anion. Now one more thing, this sodium plus ion and Cl minus ion are held together by electrostatic force of attraction. So what is electrostatic force of attraction? So you must have studied in physics. So it is directly proportional to product of the charges. That is, suppose Q1 is a charge, then magnitude of Q1, magnitude of Q2, and inversely proportional to distance between them. So keep this formula in mind. It will be used later on to explain the bonding in this ionic thing. So this kind of force of attraction exists in this ionic solid, where the charges will be mainly responsible for the stability of these ions. And why it is so, that they attract each other? Because they are oppositely charged. Now how we will explain the covalent bonding? So in covalent bonding, first of all, it is that the means this covalent bond is directional in nature. Yeah, this is true. You know that because you must have seen in the whisper theory, or if you have not studied, then you will see it that the atoms are present in a specific direction and not random sites, but not on random sites. Here is a small point here, it is very important. So if you want to know that whether compound formed is covalent or ionic, means it is majorly covalent or majorly ionic, then you can know it by seeing their difference in electronegativity. So for ionic compound, so for those of who are not aware about what is electronegativity, it is nothing but the tendency of an element to attract an electron. It is as that simple as that. So many scientists have given different formulas to calculate like the Pauling scale and different scale. But in simpler word, you can say that it is the tendency of an element or a species to attract an electron. Now, what is the difference in this electronegativity difference between the two elements for ionic and compound? So for the ionic compound, the electronegativity difference is large. So large electronegativity difference. While in covalent compound, you have small electronegative difference. So by looking at this, you can get actually means you cannot clearly say that yeah it is ionic or covalent, but by comparing you can say that okay this is more ionic or this is more covalent. You can say that by comparing the electronegativity of the two elements that are forming the bond. Now this shared pair of electron is represented by a dash between the atoms. So you will see this point later on in the sphere theory also. Covalent bond can be polar, non-polar depending upon the electronegative difference. So it is like this. So you will see this polarity more clearly in this upcoming lecture that is scheduled tomorrow. But let me give you a brief idea about that. That it is said that covalent compound can be polar or non-polar. So if a compound, suppose we have say like this, consider the example of HF. So if you see here that it is a covalent compound, but although it is a covalent compound, there is a large electronegativity difference between these two. So if you see here, then it will develop a partial negative charge due to displacement of electron towards fluorine. On the other hand, this hydrogen will develop a partial positive charge due to the movement of electrons from hydrogen to fluorine. And we will see a dipole moment between H to F. So if you put a positive charge here, it will move from positive to negative. So you will get this thing here. So this is the meaning of this polarity. Now let us see this ionic and covalent mode in more detail. Before that, let us discuss some parameters of this means bond. So yes, we will move to this ionic and covalent later on. But there are many parameters that are there in this compound, like the bond angle and the bond order, and many more things. So you know about this bond angle and bond length. So I will not discuss them very deeply. So we'll directly move this to this bond order. So it is quite important here. So what is bond order? Let me explain it. So suppose if you are given a compound like this CO2 example only. So you have seen that we are sharing two electrons. Yeah, that is right. So what is the bond order for it? So there are two bonds are formed. So the bond order is 2 here. So it is as that. It is as simple as that. But this thing will get complicated as we will move to more complex compound, and they are solved easily by this molecular orbital theory. So it has a bond order of 2. Now, what are the consequences of this bond order? So, what is the significance of this bond order? Yeah, this is the definition in the anti-bonding molecular orbital. So, we will see the definition later on. So, what is bond order? So, what are the significance of bond order? So, if the bond order is decreasing in this direction, suppose we have an AB compound. So, first it has single bond, then it has double bond, then it has triple bond. Then bond order will increase in this fashion, while as the bond length will increase in this fashion. So this is the thing here. So the same thing is written here, that there is an inverse relation between bond order and bond length. Now let us solve a question to get the idea more clearly. So we do have a compound here, 4 compounds here. That is NO, NO plus, O2 and NO minus. So this thing is more explained clearly using the MOT, but just to show the physical significance of this bond order, I am telling you this example. So if you have NO, then NO is formed like this. So you will see some curious example here. So we have 4 compounds, that is NO, then we have the NO plus, then we have the O2, then we have the NO minus. Then how I will solve it? So suppose this nitrogen is deficient, so it is having three less electron. As the octet is its valence shell theory is, valence shell electrons are 1, 2, 3, 4, 5, 6, and 7. Sorry, 5. 1, 2, 3, 4, 5. So it can bomb so it needs more 3 electrons. So it will do it in this fashion. So first of all, it will share these electrons like this. And then this oxygen will donate an electron like this. So this is a different kind of bond. Okay. So 1, 2, 3, 4, 5, 6. In this way, this oxygen is only donating its electron, but it is not taking it back from the nitrogen. So it has a total of 3 bonds. So like this, we can write that is NO like this. Okay. Now again we have a different example here. That is NO plus. So NO plus will be like this. 1, 2, 3, 4. Now it will need total of 4 electrons. So it will make a bond like this. First of all, it will get it like this. Then again oxygen will donate 2 electrons directly. It will form a compound like this. 1, 2, 3 and 4. Then we have oxygen. It is simply O2. Then we have NO minus. NO minus is like this. So we can see here that NO plus is the strongest one here. So it will have the largest bond order. Sorry, the largest bond order, and the bond length will be smaller. So it will have the smallest bond length. So this is the correct answer. Okay, so let me make one thing clear here, that it is not an accurate explanation. I'm just for an example to show the significance of this bond order. So when you will move to this molecular orbital theory, you will get a proper idea about this bond order. So what is this bond order? Simply here I am given a small example to show it. Now next we will move to resonance. So what is resonance? So if you take a compound, suppose we take a compound like NO3 minus or O3 like this. Suppose we form a compound O3 here. Then it will have two bonds to complete it octet. Now it will donate one electron, similar in the similar fashion we have seen. So one electron will be of this oxygen 1, this is oxygen 2, this is oxygen 3. So it will form a kind of like this type of compound, in which this bond is formed by the electrons of this oxygen only. Means in this bond there is no electrons of this oxygen. This is 1, 2, 3, 4, 5, 6. All of his 6 electrons are not participating in bonding, rather than this oxygen, like oxygen 1 is donating electrons, that is both of its electrons to this oxygen. So here it will be the first of this electron, then second electron, third, fourth, fifth and sixth. Similarly, if you draw it by a circle, 1, 2, 3, 4, 5 and 6. So as it is donating electron, it will have a positive charge and it will have a negative charge. So this donating of electron can happen from this oxygen to third one also. So you can see that two structures are possible. So this resonance is same. So it says that when one structure is not able to completely explain the properties of a rose compound, then we draw multiple structures, and these multiple structures are called as resonance structure. And using this resonance structure, we explain the actual structure. So how is it so? So if you write the second resonance structure, yeah, so one more thing here, that these two resonance structure will be kept apart by putting this double-headed arrow in between. So it is an important representation that is used. So if two resonance structure are present, then they will be separated by a double-headed arrow. So in this case, I am donating electrons from oxygen 1 to oxygen 3 rather than 2. So now in this case, it will have a positive charge, while this oxygen will have a negative charge. So these two resonance structure are possible for ozone, that is O3. And this is resonance structure 1. This is resonance structure 2. So if you want to get a grasp of this, how this resonance structure are drawn, you have to solve as many example as you can to get the idea. Now this second concept is called, that is, resonance hybrid. Now one more thing is written here, that the resonance structure with the lowest energy, the most stable. Yeah, this is important here. So we have seen that in the previous slide, that we have two of this thing of the ozone atom. Okay, but out of this two ozone atom, two ozone structure, that is this one, two, and this one, two, three, one, two, three. One of the structure can be more stable. So it is not the case for this compound. There are many compounds whose resonance the structure are not same, means are not same in energy, you can say. But the most stable one is the most contributing one, means it is representing the actual structure more properly than the other one which is less stable. So if you want an example, then you can take it of benzene also. So benzene has also two regional structure, so it can be like this or it can be like this. So first the double bonds are present between 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So in this, double bonds are present between 1, 2, 3, 4, and 5, 6. While in this case, double bond is present between 2, 3, 4, 5, and 6 and 1. So these both have a different structure, but they do both are the regional structure of benzene 1 and 2. And they both resemble benzene in some way, but since this structure is almost similar, so they will have the same energy, that is energy of 1 is equals to energy of 2. So they both will contribute equally to the actual structure of benzene. But in this regional structure, neither of them are able to completely explain the properties of this compound that we are dealt with. So for that thing, we are having a thing that is called resonance hybrid. So what is resonance hybrid? So it is nothing but a combination of all this valid resonance structure, and it is the most stable one of all of this resonance structure. So how is it so? So if you take the previous example O3, so it will be like this. So if you want to draw the resonance structure, then O, it will be represented by a dash line, because as this bond can be here also or can be here also, so it can be here also and can be here also. So we have taken a middle path. So do not take the words literally. I'm just using it to explain the things. So we have just taken a middle path in which neither electron is present here, but and neither here, but are present in half and half portion. So if you want to calculate this thing called uh, bond order between this, so it will be 1.5, as zero point 0.5 is present here and once one bond. Similarly, this is also 1.5 for this bond also. Similarly, if you draw the resonance hybrid of this, okay, so this thing is called as resonance hybrid. Resonance hybrid. So it will be like this. It is a very popular structure. Or it is represented like this also. But generally, we take this structure more common. That is the most common structure we take out of benzene. So it is the resonance hybrid. So they both are not different. Do not get confused that it's a different structure. They both are a way of resembling thing. But since benzene is used in organic chemistry most often, you cannot draw the structure each time. So we use a more common structure, that is this one. So this is also the resonance hybrid. Now let us draw the resonance structure. So how I will draw the resonance structure? So for this, some points are to be kept always in mind. The first point says that, okay, so if whenever you draw a resonance structure, do not change the position of the atoms, rather than we only change the position of the pi bonds and the lone pair. So what does this mean? So again, let us take a different example. Suppose we are having CNS. So CNS is like this. Okay, so CNS is like this. So nitrogen is here. I think NCS can be more better example. So NCS or CNS also CNS. So sulfur requires 2 electrons. It also requires 2 electrons. So it will be minus charge because we have to complete the octet. So CNS minus like this. Now this structure can be of different form also. So it can be like this: S minus C, then N. So in both this resonance structure, we can see that CNS is formed. Now what was the point? The point was that we only the movement of lone pair or the pi bonds take place. So this is the lone pair here. So it simply moves in this fashion, and this goes to the sulfur. So you can see that there is a movement of lone pair. So lone pair movement is shown here. This is the lone pair. And this one is the bond pair. But no sigma bonds move in this resonance structure. So this should be kept in mind as this sigma bond, sigma bond sigma bond will not be broken. Will not be broken. And due to this reason, so since one bond is always present between the two elements, so there is not the freedom for the atom to move here and there from one resonance structure to another. So with this, we move to the second point, is that sigma bonds are never broken, and because of this, atoms must remain in their same position. Now the third point, which is the overall charge of the molecular ion must remain the same. So if you see these two compounds, so this one has the overall charge of -1, -1. Also, this is also have a negative charge here, which is of -1. So this magnitude of overall charge on the compound, so do not get confused that an element is having a different sign in the different magnitude of charge initially. We will take the whole compound as a means whole compound charge. So it will have a negative -1 charge, and it is also having a -1 charge. So during drawing a resonance structure, the magnitude of overall charge, magnitude not, you can say that overall charge directly. The overall charge will never change. Whether it is plus or minus, it will be plus or minus same, and the 1 or 2, it will be 1 or 2 same. So this is the third point. Now the fourth point is that the number of unpaired electron is also same. So suppose we have a species like radical. So for those of you who don't know, so radical is nothing but an unpaired electron. So the electron is not paired, means there is no another electron that is present to pair it up. So suppose we have a alkyl radical like this. So I'm taking a typical example here to explain this radical. So do not get confused. Those who are don't not aware of it. So you will see that what is radical in the coming chapters. So in the coming lectures in the organic thing. But for now, let's just take that it is a radical that is present. So it will have 1, 2, 3, 4, 5, 5, and Suppose it will form a kind of, you can say, this kind of a radical species that is formed here. So if you draw the resonating structure here, so it will be like this. So this will move here, this will also move here, and this will move to this carbon. So this is the second resonance structure of this compound. So I'm not drawing this hydrogen. So it is CH2 also. This is also CH2. Sorry. Yeah. So it will be like this. So these are the two possible resonance structure of this C3H4 radical. So in this case, you can see that this electron is unpaired here. So the number of unpaired electron is 1. Number of unpaired electron is 1. And here also, the number of unpaired electron is 1. So this will remain same. This is the fourth rule. Now the fifth rule is that each atom should have a complete valence shell. Yeah, this is important to check. So although this rule is now getting not applicable to the compound that are not stable. So the first example you will come to see that this radical is not stable due to the reason that it does not have a complete octet. So it is not possible to draw a complete octet. Already it is unpaired. So if you take back the example of CNS, so it was like this: C N S, one negative charge, then N C S, negative charge. So this both have a complete octet. So one negative charge, which means that 6 electrons, 1 2 3 4 5, 1 2 3 4 5 6. So the both are present in bonding here. Now it has 4 electrons, 1 2 3 4 5 6 7 8. Again we have sulfur, which is 1 2 3 4 5 6 7 and 8. So its octet is complete for all of the elements. So if you take this example also, this resonance structure, that is 2, this is 2. So it will have 1 2 3 4 5 6 7 8. For carbon it will be 1 2 3 4 5 6 7 8. And for sulfur it will be 1 2 3 4 5 6 7 and 8. And it is a negative charge, so it will have an extra electron. 1 2 3 4 5 6 and then 7 and 8. So in both this resonance structure, you can see clearly that the octet of each of this element, that is nitrogen, carbon and sulfur, for both the structure is completed, that it both have 8 electrons. And the last one says that each resonance structure is separated by this double arrow. Yeah, this should be written first, sorry for that. So this should be in the middle of each resonance structure. So if a resonance structure has, if a compound has 3 resonance structure, that is A, B and C, so they will be separated by a double-headed arrow. So let us take another example like NO3 minus to see what is resonance structure. So if you want, you can write it like this. So it is NO3 minus. So NO3 minus. I'm writing all 3 oxygen with different colors. So it is O and it is a different O. Similarly, we have a N. So how we'll make the bond? So first we'll make the bond here. So how it will be? So this nitrogen will need 3 electrons first of all, and this oxygen will need 2 electrons. So it will take it like this initially. One, two, three. Now nitrogen cannot form further bonds because it needs 3 electrons only, as it has 5 electrons. Now it will start donating electron in the same fashion we have seen it earlier also. So it will donate like this. So NO3 minus we have. So 1, 2, 3. So one negative charge will be present here. So why I'm putting this negative charge here and there? So do not get confused in that. So if you get to see more and more example, you will also get a clear idea of how I'm using this negative charge. One thing should be kept in mind that usually this negative charge is not on the central atom but is on the surrounding atoms. You can see clearly from the NCS example also that both of the resonance structure have the negative charge on the surrounding atom. Similarly, for this case also, the oxygen atom is the one who is carrying the negative charge. Now, why I'm doing it so? So, if you see here that nitrogen has 5 electrons, so it has donated 2 to this oxygen, 1 to this one. Now, it cannot form further bonds, but it has a remaining electron. So, 3, then 2 more electrons are left. So, it will simply donate both of its electrons, this lone pair, to this oxygen simply. And now 1, 2, 3, 4, then 5. Now this oxygen will need one more electron. So where it will get it from? So if you want, we can draw it like this. So 1, 2, 3, 4. Okay. Sorry for the confusion. So it will donate one electron like this. And it will form one bond here. And all see oxygen has already one electron extra. So it will complete it octet using one electron simply. So it will be 1, 2, 3, 4, 5, 6, 7, and this one will be 8. Now if you consider for all this remaining oxygen, so it will form a bond like this. So it will be 1, 2, 3, 4, 5, 6. So 7 and 8, octet completed. 1. So when it is getting from here, this nitrogen. So 1, 2, 3, 4, 5, 6, 7, and 8. So 1, 2, 3, 4, 5, 6. So you can see here clearly that yeah, we have gotten the complete octet of this, all of these elements in this octet structure of NO3 minus. So if you see the next slide, so this is the one here that is drawn. 1, 2, 3, 4, and there will be one kind of this. Now if we draw the resonance structure, then it will be formed like this, the further resonance structure. So it will be kind of NO3. So this will now make 2 bonds. Now again this oxygen will make 3 bonds. So 1, 2, 3, I'm naming it. So these are the 3 possible resonance structure. So this charge written in this fashion, remember it, negative. Similarly for this, and now this will be separated by a negative, this is a double-headed arrow, and these are the 3 resonance structure. Now this 3 resonance structure can represent the actual structure, but none of them are sufficient to explain the actual structure. So they are explained using this structure, that is this high resonance hybrid. So this one is the most stable one, as this pair of bond pair electrons are distributed over all of this. So 1 by 3 is present in all of this. 1 by 3 is present here, 1 by 3 is present here, and 1 by 3 is present here. And of course this electron, electron, electron. So this is the resonance hybrid having the complete resonance structure. This is complete means a stable structure to represent the NO3 minus. So this is the example. Now let us move to a next concept, that is calculation of formal charge. So how is it done? So this formal charge is important, so you will see its significance when you will determine the resonance structure of the compound. So its formula is like this. So it says that number of valence electrons minus number of lone pairs minus 0.5 into bonding electrons. So let us take an example to explain it. So again we will take a simple example, that is CO2. So if you see here, the number of valence electron is how much? So it will be 1, 2, so 6 for carbon, 8 for this, 8 for this, 6 at 14, 14 and 8. So it will be 22 valence electrons. Next is number of lone pairs. What is the number of lone pairs? 1, 2, 3, 4, 5, 6. Sorry. 1, 2, 3, 4. So number of lone pair on carbon is 0. And then 0 0.5 into bonding electrons. Okay. So this formal charge is for calculated for each of this separately or for a compound also if you want. So if you calculate the number of lone pairs, so it is nothing but 1, 2, 3, 4, 5, 6, 7, 8. So 8 divided by 2. So 2 electrons forms a pair. So 4 lone pairs. Then we have 0 0.5 into bonding electrons. So how much number of bonding electrons we have? We have 1, 2, 3, 4, 5, 6, 7, 8. So 8 bonding electrons we have. So if you get this all two and put your formulas here, then you will get the formal charge as 0. So what is this formal charge? Is nothing but the overall charge that is present on this CO2. Okay. So in this fashion, you can calculate the formal charge on any compound. So this is not the way. This is the way to calculate the formal charge. So they are calculated for. Let us calculate it for each atom individually. So how we will calculate? So what is the total number of electrons it has? So it has 4 electrons, valence electron. And what is the total number of bonding electron? It is also 4. So 4 minus 4, that is 0. So 0 formal charge is present on carbon. So if we calculate for oxygen, then it will be 6 number of this valence electrons. Sorry for this lone pair. It will be not lone pair. What will be lone pair? Yeah, lone pair electrons. That is right. So 6 minus 6, again it is 0. And again for it is 6 minus 6, 0. So the overall charge on this compound will be 0 plus 0 plus 0, that is 0. Okay. So in this way, you can calculate the formal charge on any compound by calculating the formal charge on this elements individually. So if you go by the formula, you can do it again. So let me explain it more clearly. So some of you have got confused because how it is calculated for compound, how it is for element. So let me make it more clear. So let us do it one by one. So let us name it for 1 and 2. So for carbon, we can write it as. So the number of bonding pair is 1, 2, 3, 4, 5, 6, 7, 8. So bond pair is 8. 8 bonding electrons. How is it 8? Because I am considering this one also bonding electrons. Lone pair is 0. 0 lone pair electrons. And we have valence electron as 1, 2, 3, 4. 4 valence electrons. So if you calculate this formal charge, so Fc on carbon, so it will be bonding electrons minus lone pair minus 0 point, sorry. So it will be valence electron minus lone pair minus 0.5 into 8. So it will be simply 0. Similarly, if we calculate it for oxygen atom, so oxygen has how many bonding electrons? 8 bonding electrons. So it will be same because octet is complete. Lone pair. So lone pair electrons are how much? So 1, 2, 3, 4, 5, 6 are this involved in bonding. So 4 lone pair electrons. And what are number of valence electrons? So it was 6. 6 valence electron. So formal charge on oxygen 1. This is oxygen 1. It is 6 minus 4 minus 0.5 into 8. So it will be 6 minus 4 minus 4. Sorry, this. Okay, so you will get it as 0. So this is the thing here. Now, if you calculate it for this oxygen too, you will get it also at 0. So the overall charge is formal charge on carbon plus formal charge on oxygen 1 plus formal charge on oxygen 2, which will be 0 plus 0 plus 0, that is 0. So this is the thing. Now, how to find the most stable structure of all? So, if you are given a some compounds, some resonance structure of a same compound, and you are told to find the most stable structure, then you will do it in this fashion. So, first you will calculate the formal charge. So, the one with the least formal charge is the most stable one. So, this is the given in hierarchy. So, you will follow the stepwise, and then you will get the most stable structure. First of all, you will see that whether the resonance structure, all atoms have completed their valence shell or not. So this already there. Then second, you will see that if that resonance structure has the least formal charge or not. Then you will check that if there is a kind of formal charge, suppose it is not 0, then whether it is on the most electronegative element. So if it is on the most electronegative element, then it is good, then it is more stable. Or if it is present in the least one or the not the most one, then we will look for that resonance structure in which the negative charge is on the most electronegative structure. Now the fourth, we will see that where is the positive charge. So if the positive charge is on the least electronegative element, then it is good, either it is not good. Now if there is a charge, so suppose we have a positive charge and negative charge, so their separation should be less. So suppose we have a compound like this, A, B and C, the resonance structure is like this. In first, the negative charge is here and the positive charge is here, while in this case the negative charge is here, sorry, B, A and C. This negative charge is here and positive charge is here. Then this one will be more stable as the separation between the opposite charge is less. And for the similar charge, this should be far as possible. So if this is negative and this is also negative, then in that case this one will be more stable. And the last reason is that so if the two structures are equivalent, like the structures of ozone, so they will be equally stable. So let us see this example here. So it says that which of this is more stable. So first of all, we will see that whether its octet is complete or not. So it has two negative charges. So it will be 2 plus 4, 8. Yeah, this is complete. This is also complete. For similar, you can see for this. So both of these have a complete octet. Then second, you will see that which of these has a less formal charge. So if you see calculate the formal charge, so it will be 2 minus 1, that is 1. And it is also 2 minus 1, that is 1. Now you will see that which one of these has a less separation of charges. So this one will have a more. So this two negative charge are present here and positive charge. Well, in this this thing is different. So you can see here clearly that the negative charges are separated more. This one. Also, the negative charge is present on a more electronegative element. Okay, so this one is more stable. Sorry. So you can see here that the negative charge is present on more electronegative element, that is carbon. So this one is more stable as compared to this. So this is the answer. So we will check that all these points in order wise to determine that which of this structure is more stable. So first we have seen the octet. So both of our octet are complete. Then we have seen that whether which of these has a greater formal charge. So we have seen that okay, so this both have the same formal charge. Now we have seen that whether this charge is present on an electronegative or electropositive element. So in this case, it is present on a less electronegative element. So we have considered this one as more stable. Next, we will move to ionic bond. So we have seen what is ionic bond. Now we will see this thing in more detail. So in ionic bond, we have electron means bond is formed by the complete transfer of electrons. And this type of valency where this complete transfer of electron take place, it is called as electrovalency. We have seen these points earlier also. Now these ions are held together by electrostatic force of attraction. So these are the earlier points. Now we will see these three things to see the stability of that ionic crystal we have. So we will see the first thing, that is ionization enthalpy. So what does ionization enthalpy say? So it says that it is the energy that is required to move one electron from the gaseous state of a metal or a non-metal. So if we see here, so this X is present in the gaseous form. So we will remove one electron and we will get this thing. So in this ionization definition, this thing is important, that the metal that we are getting the ionization potential, the equation, so it must be in the gaseous state first of all. Then we will calculate the energy that is accompanied in doing so. So this is the ionization enthalpy. Now next thing, it is represented in kilojoule per mole. Now second thing is electron gain enthalpy. So in electron gain enthalpy, what it is? So it is just opposite of ionization enthalpy. In this, we add an electron to a gaseous element, that is X. So it is present in the gaseous state. We add an electron to it. So the same condition goes for here, that it must be in the gaseous state. And it is also generally represented in terms of kilojoule per mole. Now the last one is lattice energy. So what is this lattice energy? So we have got two species that are in gaseous state, cation and anion. So when we add these two, we will get some amount of energy released. As the opposite charges are getting together, so they are getting stabilized. So some energy will be released in this process. So this both will combine to form an ionic solid. Now this lattice energy is directly proportional to charge of square of the charges. So I have told this thing to you to remember earlier also. And also it is inversely proportional to the distance between them. So you can see here clearly that it is more dependent on charge, and we are doing the square of the charges rather than the distance. So it will be helpful to determine the stability of a given ionic solid that we have. So what we have done, we have written it step by step. So we have formed this anion by electron gain enthalpy, so electron gain process. Then we have formed the cation by doing ionization to get the ionization enthalpy. Then we have combined this both of these two, in which energy is released, that is called the lattice energy. And yes, one more thing. So in this thing, you must remember that 1 mole of that compound should be formed. Okay, only 1 mole of compound should be formed. Then it is only called the lattice energy. So lattice energy. We take the gaseous cation and gaseous anion. Then we add both of them to get 1 mole of that compound to give the required lattice energy. Now, these three factors are responsible for the formation of ionic bond, and they do decide the stability also. So less is the ionization enthalpy, means less energy is required to the for the formation of that cation. It will be formed easily. That solid will be formed easily, and more energy will be released. So if more energy is released during addition of electron to a neutral species to get our anion, then the ionic compound will form easier. The third one is that more and more energy is released on after adding of this two cation and anion, then it will be more stable. So these are the criteria for stability, means the ease with which the ionic compound will form. So they are directly proportional to all of these three. In all these three, this lattice energy is more stable, in which the electrostatic force of attraction is responsible for formation of that ionic compound. So the two cation and anion will come together and form that compound. So we have an example here. So we have 4 compounds that are given. So if you see here, that if you form the ions here, that is Rb plus and Cl minus. Li plus and Cl minus. This is K plus and Cl minus. Na plus and so it will be Cl minus. So in all of this, we can see clearly that the magnitude of charge is same. That is plus for all this cation and minus for one for all this anion. But the difference is between the radius. So if you see here, the anion is same. Okay, so the anion is same, but the cation is changing. Rb, Li, K and Na. We have seen that lattice energy is inversely proportional to the bond length. So if the radius of this atom will be more, that is less will be the lattice energy. So let is the lattice energy, that means this lattice will be less stable. That is, it will melt easily. So which will melt more complicatedly, which will have the highest melting point. So which is having the largest lattice energy, and lattice energy is inversely proportional to bond length. So out of these four, so if you look at the periodic table, this sodium has the least radius, and since the anion is common, we will see the cation only. Due to this reason, this will be formed. This will be formed more easily, and it will have the highest melting point. Now suppose if I replace this by, suppose we have a different example, that is CaCl2. Then in this case we will not see the radius at all. So I am replacing, suppose this with this. You have seen that lattice energy is of course inversely proportional to bond length, but it is directly proportional to square of the charges. So the magnitude with which it is varying, it more for charges. So it will more dependent on charge. So the CaCl2 will of course have a high melting point because the charge on this Ca is 2 plus, and it is 2 of the Cl minus are released. So it will have a greater magnitude of charges, and since the electrostatic force of attraction or the lattice energy is more dependent upon charges due to the square of it, so in that case CaCl2 will be answer if this all four are mentioned here. Okay, thank you for the time. This was for today's lecture.